Hi friends, in this video let us learn about small signal parameters of MOSFET. So to understand this concept, let me draw NMOS common source circuit, right? So let us take one NMOS in common source configuration. This is VDD, this is drain resistance. Here I take drain output, and this is NMOS. I take NMOS common source. So source is common, so it is grounded, and I apply both time varying source, that is VI, and EGSQ DC source, right? So this is the point. Okay, and this is VGS. Okay, fine. Here drain current flows. Okay, so it is enhancement mode MOSFET in common source configuration, common source circuit, right? So here what we have done, here we apply both time varying source or AC, time varying or AC, that is VI, and we apply DC source, both in series, right? So DC source is VGSQ, right? So this is AC source and DC source, both are applied in series. So we assume that this is sinusoidal. Okay. So for that, the characteristics is given by, it is VDS x-axis, drain characteristics. This is ID. Okay, so let me draw this. So the characteristics will be like this. Okay, fine. So this is low line. Here you see when you take what you call the region of operation. So whatever the things coming here is non-saturation region. This and all we studied. This is saturation region, and here are VGS, right? So when you see, we will draw DC. This is DC load line. DC load line. Okay, fine. What we are going to do is, you can see that so VGS is gate voltage, is our input voltage. So when you give input like this, right, VI, what will happen to the output? So this is output. So in saturation region, this one, and this one. So you see the input is amplified. So VGS gate voltage is input, drain to source voltages, you see VDS output. VDS output, VGS is input. So this is VDS, this is time. So the signal is amplified. Here we have VDD. Okay, because what is VDS? VDS is equal to, from the diagram, VDD minus ID RD. So this is VDS. This up to this point is VDS. Source is grounded, so VDS is equal to VD. That's what we have done. So VD is nothing but VDD minus ID RD. Okay, so that's what we are understanding from here, right? So when VDS is equal to VDD, ID is equal to 0. You substitute here, VDS is equal to VDD. Here, what we get is ID is equal to 0, right? So that's what we got here. ID is equal to 0. Is it okay? So when ID is equal to 0, what will happen? When ID is equal to 0, VDS is equal to, sorry, here when VDS is equal to 0, VDS is equal to 0, what will happen to this equation? VDS 0 means this implies VDD is equal to IDRD, right? So This and all we have to understand. So ID is equal to VDD by RD. ID is equal to VDD by RD. So this is what load line about it. Okay, so when the transistor to be used in amplifier, it should be biased in this region. Right, so your Q point should lie, especially this is Q point. Fine, so this is the thing you have to remember. So whatever from here to here, non-saturation region, right? So from here to here, it is saturation region. That's what I have developed. Okay, so those things are very, very important. So from this, you can see the output is a linear function. See, when input varies, output varies proportionally. So output is linear function of input in saturation region. So there only the transistor is used as the amplifier, right? So that is what we have to remember. And moreover, another thing we have to know from the circuit diagram is total input voltage is total gate to source voltage. So VGST is equal to VGSQ DC plus VI, right, AC. So total gate to source voltage is sum of these two, right? So when EGS increases, what will happen? When VGS increases, ID will increase. That's what we know, because ID is equal to K into VGS minus VT squared, whatever it be. Whether it is linear region or triode region, ID is proportional to VGS. So when VGS increases, ID will increase. That's obvious in curve also. This is VGS more VGS, so ID is more, right, here less. And moreover, another thing we have to remember is, and VDS becomes smaller. VDS is less. The reason is, you see from the diagram, when VGS increases, right, so VD saturation will be more, but VDS will less. From the diagram itself, you can clearly understand. So these are all the points you have to remember when you are working with the transistor basics. Now we will see small signal parameter. Small signal parameters. We know that time varying source will generate time varying output, right? So what is the time varying component? See, time varying source will give time varying component. See, time varying component of VGS, right? So what is the reason? You see, we are having in the circuit, this is time varying component. This will give time varying VGS. This one will give DC, but this is time varying REAC. So when this is varying with respect to time, VGS will also vary with respect to time, because VGS is sum of these two. So what is the thing? We know that instantaneous gate to source voltage. Instantaneous gate to source voltage is given by VGS, that is the sum of DC VGSQ plus VI. Yes or no? This is easy. So that is given by VGSQ plus VGS small, right? Small means AC, time varying component. This is time varying component. Okay. Fine. So what is this is DC component. This is DC component. Okay. Right. So what is instantaneous drain current? Instantaneous drain current is given by instantaneous drain current is equal to ID, which is given by Kn, because we have chosen n channel MOSFET, VGS minus VT square, right? So let us assume this is equation number 1, this is equation number 2. Okay, fine. So what we are going to do is ID is equal to Kn, right? So in this VGS, I substitute this one. So VGS plus VGS minus VT square, right? Okay, so expand this. If I expand, what I get is Kn VGS minus VT square. These two I bring together. This VGS I keep it separately. So 2AB, 2Kn VGSQ minus VT VGS. Right, this I write as simply like this: VGSQ minus VT plus VGS square. This is A plus B. Okay, plus Kn VGS square. Right, so this is a very important point. Here we have to remember something. You see, this is DC component. You see, everything is DC. This is DC, this is DC, this is some constant DC component. Here we have, what is the thing? VGS. This is VGSQ. VGS small. This is AC component or time varying component. Because of this VGS, right? Okay, fine. So this is what this is producing harmonic component. Harmonics. This one producing harmonics, because second order square, if you square any sinusoidal signal, it will produce harmonics. What is the reason? You see sin square t, it will give 1 plus cos 2 omega t by 2. So this is second harmonics of fundamental frequency. So always square term produces harmonics, right? So what we are going to do is, from this we understand one thing. So this is unwanted term. So harmonics I don't want. Right, so to minimize harmonics, what I have to do? I put one condition. The condition is this VGS must be far less than 2 into VGSQ minus VT. If VGS is far less than, that is the signal, this is time varying component, hope you remember, right? If time varying component is very small compared to DC component. You see, this is DC, 2 VGS minus VT. What will happen? This term will go, because compared to this is very small. If you square it, that is becoming more small. So 0.1 is small, 0.1 squared is, it is very less. So this term will go away. I have compared to this term, because VGS minus VT is very big value compared to this. So this term will go away. So I have only these two components. Right, so ID has one DC component, one AC component. So total DC component IDQ. This DC component that I write as Kn VGS minus VT squared. This part is AC component. AC is small letter. So ID is equal to 2Kn VGSQ minus VT squared. Right, so you see the signal magnitude should be very small compared to this value, so that's why we are calling it a small signal. So now we define a new parameter called transconductance, GM is given by ID by VGS, right? So okay, so this is 2Kn VGS minus VT, VGS, not square. So ID by VGS. So what is ID by VGS from this? ID by VGS equal to 2Kn VGSQ minus VT from here, right? So this is very, very important parameter. This is one of the small signal parameter, transconductance, right? Otherwise, you can define transconductance also dou ID by dou VGS, capital ID. Capital ID means this fellow. If you differentiate this, what you get with respect to VGS, I will get the same answer, 2Kn VGSQ minus VT, both are same only. Right? So I know that. So from this, what I understand, GM is equal to 2 root of K ID Q. What is the reason? Because I know ID is K into VGS minus VT square. This implies VGS minus VT is equal to root of ID by K. Right? So substitute this one here. What you get is this one. Right? So if we substitute this equation, instead of VGS minus VT, we substitute root ID by K. I get 2 root of KID. So this is very, very important. All the two equations. This is one of the important equation. This is another important. So A, this is B. Right? These two equations are very important. Okay. Fine. See, from this, what we are understanding is GM is equal to 2KIDQ. Right? From this, what we are understanding, transconductance is directly proportional to K. GM is a function of K. What is K? It is a conduction parameter. Right? So what we learn from this one, we know conduction parameter is given by K is equal to 1 by 2 mu n C mod x W by N. So it is a function of K is a function of F of W by N ratio. So by changing the width or by changing the length, we can change the gain or transconductance. Why it is called gain? Because it is relating ID by VGS. So ID is output current divided by input voltage. VGS is input voltage. It is relating current output by input, so it is gain. So transconductance. So transconductance can be varied by changing the width to the length ratio of the transistor. Right, so that is one of the important points we are learning from this, right? So, and you see from VGS ID characteristics, that is transverse characteristics, VGS ID, we know that when VGS is less than VT in N-channel MOSFET, VGS is less than VT, that diode or transistor will not conduct. So up to this, it will not conduct. Let us assume it is VT. Beyond that, it will start conducting, right? That's what we know. Okay. So this is VGS, this is ID, and you see the slope of this curve, ID by VGS, right? What is a GM? Change in ID divided by change in VGS. So change in ID with respect to change in VGS. That is given by transconductance. So transconductance is slope of this curve. Slope of curve, which is nothing but transconductance, right? So that is the thing. So when you have an input-output relation like this, right? So when you give this one, what will happen here is, okay. So this is a Q point. Right? So you see when Q point is in saturation region, right? See ID and VGS are linearly related. When there is a change in VGS, there is a change in ID. Proportional, linear. You see when this is changing linearly, the output is also changing linearly. Under what condition? When Q point is in the saturation region, right? So then only, see when VGS is greater than VT, and you see then only the transistor will be on. For saturation, VDS must be greater than VDS minus VT, right? So VDS sat. So under this condition, there is a linearity between the input voltage and output current. So transistor works as an amplifier. So GM is the slope of the curve, right? So if VGS is very small, if VGS is small, then transconductance is constant. That's what we have said. So VGS is very small, change in VGS. So from here to here, let us assume if VGS is very small, the transconductance will be constant. That is another important point we have to know. So when this is slope. If you draw any line tangential to this curve, then that will be called transconductance. So when VGS is small, the slope is or the transconductance is constant, right? Okay. So when Q point in saturation, so in our diagram, the Q point in saturation, when MOSFET operates as current source. MOSFET operates as current source because in saturation current is constant. So current source. Right, so that is another point we have to remember, right? So when Q point moves away from saturation, Q point moves away from saturation, then what will happen? MOSFET no longer operates as current source. These are all the points we have to remember when you are learning the small signal parameters of the MOSFET. Thank you.